We have two presentations of Rehas and Han. So Rehas will present about YOLO object detector, and also Han present about hyperparameter tuning. And I think I will leave it to you guys right now. So Rehas, you can start.
Okay. So my screen is visible.
Yeah.
Okay. Um, so my today's presentation is about the YOLO algorithm. It is an object detection algorithm which we will be using further in our project in the car part detection uh, model. So, so YOLO is a very popular algorithm. Uh, its popularity is basically due to because it's very fast and very accurate when compared to other object detection models like fast RCNN and faster RCNN. So first we will understand what is object detection. So object detection, as we know, is a phenomenon in computer vision that involves the detection of various objects in digital images or videos. It answers to basic questions, tries to answer two basic questions. That is, what is the object? What is the object that we are going to detect or we want to detect in a video or an image? And where is that object? That is, where is the location of that object in a certain image um, or in a certain frame of a video? So, object detection consists of various approaches such as fast RCNN, retina net, single shot multi-box detector. These are various other algorithms which are used for object detection. So, YOLO algorithm gained popularity because of its much superior performance when compared to other uh, previously known models used for object detection. So, next we will understand what is YOLO. So YOLO is abbreviated as is an abbreviation for the term "you only look once." Uh, as the name says, we only have to pass the image once through the network for it to fully detect the location and the type of object in an image. It solves a regression problem when trying to detect the when trying to print or give the output of the bounding boxes of the image. Also, YOLO employs convolution neural networks to detect the objects in real time, and because it's just look only once, it passes only a single forward pass is needed for an image uh, for it to detect the objects. And it consists of various other variants too, like YOLO and YOLO V3. There are various other models of YOLO too, like YOLO V4 and YOLO V5. Uh, Lots of progress has been made in improving the uh, first basic known YOLO algorithm. So now we will understand how the YOLO algorithm works. It has three basic techniques. One is residual blocks, then we have bounding box regression, and then we have intersection over union. So we will see each of these terms one by one. So in residual blocks, what are residual blocks is that we divide the image into grids, and each grid is of a dimension of s process. So as we can see, we have divided a given image into various grids, and then we try to detect an object in each cell or each cell of this grid. In the image, there are many grid cells of equal dimensions, and every grid cell will detect objects that appear within them. For example, if an object center appears within a certain grid cell, then this cell will be responsible for detecting it. So it detects the center of the on object, and if the center lies in a certain cell, then that cell is responsible for the detection of that object. Next is bounding box regression. So bounding box is an outline that highlights an object in an image, and every bounding box in the image consists of the following attributes: the width of the bounding box, the height, the class, that is what class that bounding box represents, and the bounding box center. Other than that, there is one more probability, that is the probability that there is an object uh, present in the given cell. So the center of the bounding box, that is Bx and By, it is calculated with respect to the given cell. That is, its value lies between 0 and 1. Both the coordinates values lie between 0 and 1. While the width and the height of the bounding box, it is relative to the whole dimension of the image. So its value is to be understood with respect to the entire dimension of the image. If the width is 1.5, then it's 1.5 times the dimension of the width of the image. And similarly, we can understand that for height too. And the class is the class is the which class the given bounding box, it gives the class scores of all the possible classes that we're trying to predict. And PC, that is the PC value that is being that the model predicts is actually the score, that what is the probability that there is an object in the given cell. We will see more this later. Next is intersection over union. So this is also an important concept which we will require when we will try to uh, get to know the scores of the various like how the model is trying to know which bounding box is giving more accurate prediction. So it is calculated with this metric that is called intersection over union. So it is defined as the area of overlap, that is the intersection divided by the union. So we can see that its value is perfectly 1 when the predicted bounding box completely overlaps with the target bounding box, and its value will be 0 if there is no overlapping at all. So this is an important metric which we will see further how it is helps us to determine which bounding box is more closer to the image. Next we will see. So like in this one, the for this given image, the green bounding box is the actual target, and the blue bounding box is the printed target, that is the predicted target. Next is the network design. So in the original paper, they have used 24 convolutional layers followed by 2 fully connected layers. And one thing that they have done in the original paper is that they have trained the network, pre-trained the model on ImageNet data, and from then onwards they increase the dimension from 224 cross 224 to 448 cross 448, and then they trained this model for the YOLO use case. So we will see now how the output is being predicted and what does the output consist of. So each grid cell predicts B bounding boxes and confidence scores for those boxes. These confidence scores reflect how confident the model is that the box contains an object, and also how accurate it thinks the box is that it predicts. Formally, we define confidence as probability that there is an object multiplied with the intersection over union of the truth and prediction. So if no object exists in the cell, the confidence score should be 0, and otherwise we want the confidence score to equal the intersection over union between the predicted box and the ground truth.
Can you make
So
one more slide
yeah,
before that about the network structure?
yeah,
So the final structure is 7 by 7 and by 13,
30,
right?
yeah.
So which
So
means they divide the image into 7 grid, 7 by
yes,
7
yes,
grid.
yes, yes, yes. They divide the image into 7 cross 7 grid, and here 30 is for we will see 20 here is in the 30. 20 is the class probabilities, there are 20 classes, and 10 is coming from there is a formula for that. There is two bounding box and 5 predictions for each bounding box. So 5 into 2 is 10 and 20 plus 10 is 30. That is how it is being
I think
predicted.
you should introduce first. So when did they try to regression in the seven grid?
Yeah, yeah, it is in the later slide. I will show that one. And let me see. So in each bounding box, there is 5 predictions. X and Y is the center of the bounding box that is being predicted, whereas width and height is the dimension of the bounding box. And finally, we have the confidence. The xy coordinates represents the center of the box relative to the bounds of the grid cell, and the width and height are predicted relative to the whole image. Finally, the confidence prediction represents the intersection over union between the predicted box and any ground truth box. So that's how there is a 5 prediction for each bounding box. And in the original paper, they are predicting 2 bounding box per cell of the grid. So each grid cell also predicts C conditional class probabilities.
And
That
can
is
you slow it down a little bit? Make one more slide. So,
this one.
so the confidence is the P, right?
Yeah,
It have object in it or not? The PC.
yeah, yeah. If the object is there or not, PC. And after that, there is also class probabilities. Okay. So, so there is also C conditional class probabilities. So like for each cell, total it becomes um, uh, C conditional class probabilities. That is probability that there is a class given that there is an object, and these probabilities are conditional, uh, and we only predict one set of class probabilities per grid cell regardless of the number of the boxes B. So then this is the formula that they are using for calculating the probability of the class. I don't know how they came up with this formula, but it seems like they are using Bayes theorem for this one, and I'm not sure about that one. And for this part, the probability of the, like for calculating the probability of a class, they are using Bayes theorem, and then they are multiplying it with the intersection over union to uh, so that both the values are encoded. Like they have said, these codes encode both the probability of that class appearing in the box and how well the predictive box fits the object. So both of them are get captured. It might happen that the model predicts a very good probability of a class, a very high probability of a class of object, but the bounding box is not accurate at all. So in that case, we would want our prediction to be very close to zero. So that's why I
Oh,
think they have multiplied it with in intersection over union here. So this is how they have done this. This is the visualization that they have done on the paper. Bounding boxes plus confidence, and they have a class probability map, and using that they are calculating the final predictions. Here is the formula for each. If we have split our image into S cross S grid, then for each S cross S grid, we have B into 5 plus C predictions, where B is the number of bounding box. For each bounding box, we have 5 predictions, that is width, height, center, and uh, the width, height, and the center of the uh, uh, object and the class probability score plus uh, the plus the probability of the various classes that the object is the model is trying to predict. So based on that, we then have wait a second. Yeah. So the centers is not the center of the object is not a single prediction. It is actually XY coordinate. So that's how it is total 5. Hope that is clear. Okay. So that was all for the model here. Next, applications of YOLO. So YOLO algorithm can be applied in the following fields like autonomous driving, and uh, we use YOLO in automated cars to detect objects around traffic like peoples, vehicles, trees, etc. Also, it is used in wildlife to detect various types of animals in forest, and it is used by rangers and journalists to identify animals in videos, etc. And finally, it can also be used for security, such as security systems, where we can like uh, detect if people are trying to trespass or something like that. So these are the various applications of YOLO. There can be even more applications. Uh, it can be used almost anywhere. Next is, so the finally to summarize, we gained an overview of the object detection and the YOLO algorithm. We went through the main reasons why the YOLO algorithm is important. We learned how the algorithm works, and we also gained the understanding of the main techniques used by YOLO to detect objects, and we learned the real life applications of YOLO. So that was it. So, you have any questions?
I think you meet the loss function in this paper, right? So it's very important part of your.
Oh, yes, I think I forgot to put in here.
So you still not fully understand about the loss function, right?
Yeah, actually, yes, I forgot to put it here. Let me see if I can bring the paper here.
So we can do it later. Now let people
Okay.
ask questions about what.
Okay, I tried to implement the code here for the YOLO on Colab.
So can you back to the slide a little bit so people can ask the question
Okay,
about
yes.
slide first, and then we can demo later. So anyone have question about it, or
Yeah.
maybe not clear?
Hi.
Yes.
Uh, I understood the bounding box and IOU, but can you go back to residual block? The first slide, I guess. Yeah. Can you repeat this for me?
Yes, so the image is split into a grid of S cross S dimension.
Okay.
It depends on us how much small we want, and I think if the smaller it is, I think the smaller it is, the better the detection is for the objects, but it also is more computationally expensive, but it gives better result. So this is what we do. We split the image into S cross S grids, and each of these cells of these grids is then responsible for predicting a bounding box. And we try to match this bounding box. That is, we try to take and calculate the IOU or with the target bounding box and see how relevant this bounding box is to our target bounding box.
Okay. So the name residual block is for basically for since we divide S cross S grid
Yes, yes,
and they form a block.
yeah,
Oh, they call blocks. Okay, I'll look into it. Yeah, that's all I wanted to ask.
yeah. So any more questions? Like Hang, would you like to ask something?
About Hang and Home. Do I have any question?
Em học tiếng Việt đấy.
Yeah, okay, you can speak Vietnamese.
Kiểu như theo em hiểu ấy thì cái cách mà cái YOLO này dự đoán là đầu tiên là nó dự đoán nó chia cái ảnh ra thành từng cái ô thành thành n ô nhỏ, sau đấy rồi nó sẽ dự đoán trên từng cái ô nhỏ đấy. Sau khi dự đoán xong rồi, tức là cái ô ô tọa độ 11, tọa độ 12, tọa độ 13 nó sẽ có nó dự đoán được xác suất rồi ấy. Rồi mỗi từng cái ô đấy nó sẽ lại có nó nó sẽ có một cái giá trị dự án riêng ấy. Rồi sau khi dự án xong rồi họ mới ghép những cái ô đấy lại thành thành cái ô to, đúng không? Hay
Ờ,
là
Không,
dự
họ
đoán
cứ để đấy thôi, nghĩa là giờ nhá, họ có 7 ô nhá, thì ở mỗi cái 7 ô đấy, 7 nhân 7 là 49 đúng không?
vâng,
Thì mỗi ô đấy thì họ sẽ dự đoán B cái box khác nhau, xong rồi mỗi ô đấy họ sẽ dự đoán B cái box. Xong giả sử em có một cái round chute chẳng hạn, thì cái round chute đấy có là bounding box ấy, bounding box thì cái round chute thì có một cái ô giữa, cái ô giữa mà rơi vào cái ô nào trong 49 ô đấy,
vâng,
thì cái ô mà cái ô mà fail, ô mà thế nào nhỉ? Ờ, đầu tiên em có một con mèo này, con mèo cái tâm giữa của con mèo ấy rơi vào cái lưới thứ 21 chẳng hạn, thì cái lưới thứ 21 đấy sẽ có trách nhiệm là phải predict con mèo đấy, thì em sẽ học về cái đấy.
ờ. Thế làm sao để mình tìm ra được cái ô đấy?
Thì nghĩa là con mèo đấy thì em biết trước round chút đúng không, thì em bắt đầu em tính cái round chút đấy, xong cái ảnh của mình sẽ chia là 49 ô đúng không,
Vâng,
thì em tính cái center của con mèo đấy, con mèo rơi vào ô nào, cái predict của cái ô đấy phải đoán được con mèo đấy, có hiểu không?
để nốt lại, nốt lại.
So I think we can continue about demo. And about Hang, do you have any question?
Hi. I have heard that about the size of S by S. Um, Rishabh, can you back to the rest of the blog slide? Uh, do you know the value of S here?
Yeah, in this paper, I think they have used 7 cross 7.
7 by 7.
Yeah, in the YOLOv1 paper, they have used 7 cross 7 grid.
That is so V1, right?
Yeah.
Okay. I read some at the Zolo V3 paper. They use three like three values of S, like 13 by 13, 26 by 26, and 52 by 52. It is used in case we have a different side of object, right?
Yeah.
And yeah, this is my question, because I haven't read the Zoro V1, so I I have a little intuition about the S value.
Okay.
And I think it depends on the density of the object in the image as well.
Yeah.
If have a lot of image, have a lot of object need to detect, and think we need to increase the width, or not sure, but I think it also depends on the density of the object in the image.
Yeah, so the smaller we use, the better it will be able to detect small objects.
It depends on the density of the picture, right?
Yeah.
The
How?
object in picture.
Yeah, but how you know that? How you know the density of object in the
I
image?
think this is one of the hyperparameter. Right? So it depends on the data set we training
I don't think
it.
so. I think the S value is 7 is at the version 1 of Zolo, and in the progress they have some values of S, like 13, 26, or 52. Uh, it use for all the images, like in case the image have like small object or not.
Yeah. So I think right now we have S by B object, right? So we have total of S by B, right? So we have S by S grid and X grid we predict B bounding box. Right?
B1. I think B is needed in all cases. Uh,
I think it over the hyperparameter.
okay, I need to read more. So, thank you.
And we can discuss about it later.
Yeah. So do you want to discuss the loss function, or should skip to the code?
I think we should skip to the code.
Okay. So the code was simple, uh, nothing different. However, in the tutorial that I followed, they didn't use pre-training. Uh, they just we directly trained from scratch, and I trained it for like 100 epochs or some less than that, till the mean average precision was less than or equal to 0.9. These are the some of the results, and you can see this here. It is able
So,
to, yeah, detect
so do
planes.
you have the data set in here? Can you describe a little bit about your data set and
The
how
data set.
function is using the code?
Okay. Yeah, so the data set was the same that was used in the paper. I found it uploaded on Kaggle. Wait a minute, let me see. Um, so it's called the Pascal VOC YOLO.
Okay, the part data set.
Yeah, this is the data set used.
So it is like multiple objects, or what kind of
Yes,
objects? Like you have an airplane, or like any kind of like ImageNet data set, or
yeah, there are labels and there are
100
images.
sample.
uh, click on images. Oh, maybe I could see that. Okay, so like
Yeah, yes,
any object.
yes. I don't think they have named the labels. I think they have simply given the bounding boxes for those labels. Let me see if they have name. I don't think they have named the labels. Yeah, so there is no labeling, like there's no naming of the class labels. I think they have
Uh,
just yeah, simply objects and their bounding box coordinates.
can you go back to code
Yeah,
and to the images that you predicted on? Okay, so basically any kind of object. Yeah.
yes.
Can I see the train file? Train.p file.
Can you what? Can you repeat?
As a training file, train.p, right?
Yeah. Wait a second.
The file.
You can simply open your Google Drive, maybe. That's
So these are the simple libraries that we have imported. Few utilities imported from utils.py, and here we have the hyperparameters. Uh, First we train our model with load model equals to false, and we then save our model. We use this code to save our model. We check if the mean average precision is greater than equal to like 0.9, then we save our model, and next time when we load our model, we use this code to uh, plot our bounding boxes from the predicted model.
It was industrial. I think the most important part is that I think a lot of B file.
Yeah. Some of this was like directly provided. Like here, the tutorial, there was not much explanation for the utils.py, and most of the training was like copied or like directly implemented without much info into it. So I had to follow along with that, and I then simply I understood how much like he explained, and then later I just copied the code. Yeah, actually, this is the code for like predicting the bounding box, I think.
So what is the input of loss function here?
Input of what?
A loss function.
Loss function. I think there is another file for loss.py. There is mean squared loss, sum of square radius residuals, something like that. It's called. That is what is being used in the paper.
The forward function. Forward.
Can you repeat?
I think YOLO have. I think I already told you YOLO have just two important things. So first thing about the reconstruct the grid, and second thing about their loss function. They're quite unique,
Yeah.
and that you just present the first part, and the second part about loss function you not yet present. I
Yes, I
think
think
you
I did.
should add it later to next present or
Okay, I will then
meeting,
present it later in the next one. Yeah.
because the loss function YOLO is really important to the paper. It's the most important
Yes,
part.
yes, yeah, it is.
I think overall it's really good presentation. So yeah, it's quite clear about how the YOLO work and really clear presentation. Really well prepared. So I think it's really okay. Just you missing the loss function of the paper.
Yeah, so next presentation, hopefully I will implement that too.
Yeah. So I think that is from Riyadh part, right? So anyone have further questions?